So where we left it last week, we got to the end of the Pennsylvanian period. All right. There's one more period that we need to go through to get all the way to the end of the Paleozoic era. Remember, the Paleozoic stands for what, Clayton? Time of ancient life. Yeah. We're about to go into the Mesozoic, the time of middle life. And then this coming Thursday, we will devote our attention to the time of recent life, the Cenozoic. So by today's class, we should go all the way from the end of the Pennsylvanian all the way to the end of the Cretaceous. We're going to hit the KT boundary today. But before we do, I want to briefly touch back up on sort of where we left off last week. You remember from the first lecture that I gave in this semester, we talked about an unconformity. We all know what that is now. There's no point in sort of rehashing that. But the reason I want to come back to this specific unconformity from the first lecture is that it's this period after the Pennsylvanian, between that and the Cretaceous, which is where we're going to end today. So I want you to keep in mind that everything from today's lecture, the beginning point, all the way almost to the end, is going to be missing from the geologic record of most of the Mid-South, okay? From Tennessee, Kentucky, most parts of northern Alabama, northern Mississippi. The record is totally missing for the Permian, Triassic, Jurassic, and most of the Cretaceous periods. It's only the little bit of the end of the Cretaceous, which is represented here by these gravel formations that you see above the unconformity. That's the only part that we really have from the Mesozoic era. Everything else is missing. And again, we'll explore a little bit about why. Now, I showed you guys where we left off. We had just gone through the process of building the second major supercontinent that we'll talk about at least during this class. And that is the supercontinent Pangaea. So roughly 300 million years ago, more or less, we have the supercontinent Pangaea. Actually, we're at, well, 290 million years, so pretty close. So that's a great test question, right? That's a great conversation question. You know, if somebody's in an elevator, hey, when was that Pangaea supercontinent? You know, you ought to be able to say with some reasonable level of comfort. It was about 290, 300, 310 million years ago, right? You don't need to be coming up with some harebrained explanation like, I think it was like 50 million years ago, or I think it was 1.5 billion years. Like, that's a wholly uninformed approach. You want to know that it's in the ballpark. Now, Pangaea was this massive supercontinent, but it definitely had islands, and it had sort of large sections of sort of where the oceans were kind of coming into, like various bays and inlets and those kinds of things. There were shallow seas, like you could see there in the Southwest. And there were also big mountain ranges. The mountains then were about the height of the Himalaya Mountains, and they were called the Trans-Pangean Mountains, meaning that they went all the way across the continent of Pangaea from one side to the other. You can see here that they kind of go across from northern South America. So where I'm kind of circling here with my cursor would be approximately where Colombia and Venezuela is today. But look how close it is to where modern day Tennessee and Alabama are, right? Very close. And then not too far away is Northwest Africa. And then what is this right here? Does anybody know what this landmass is? Antarctica? Probably, yeah. We'd have to zoom out a little bit. It's either Antarctica or Australia. It's one of the two. I actually think it's Western Australia. So that would be approximately probably where the city of Perth, Australia today would be located about right here, for example. So there's West Africa, and then of course, you've got bits and pieces of Europe and Asia that are kind of farther to the north and northeast. And actually, again, directions don't mean much now, because as you can see, the equator is now totally shifted more. We're at sort of a diagonal if we're looking at this, right? So it's important to realize the direction of north as it is today is different back then. We also said that when Pangaea was forming, that a large section of the earth was desert ecosystem, okay? It's not a modern desert because a modern desert has plants and animals that we think of today are desert adapted. It was a paleo desert. It was an ancient type of desert that was dominated by very different life forms in some cases than we see today. So we'll talk a little bit about that. Now, one of the things that involved with Pangea that we see is the way that through these orogenies, these mountain building episodes, these layers and layers of crustal rocks, the rocks that form the crust, how they were more or less deformed and heavily folded and faulted, okay? I want you to take a look here at this bottom diagram, and I want you to let's go through it in sequence, just so you can sort of see that. Number one, on the far left side, notice here that the squeezing forces the various layers, the strata, to sort of bend upward gently, almost like you would expect with the creation of the Nashville Dome or the Cincinnati Arch or the Pascola Arch, right? You get these upward sort of anticlines that we've been talking about. And then when you exert pressure, that might happen for a variety of reasons. It could be that you have two land masses sort of bumping into one another that are forcing that tectonic plate to just sort of buckle up, right? But what happens when the force of that collision is stronger in one direction than another? So like if you have Africa bumping into North America at a very strong but slow rate, then that force becomes lopsided and it begins to push that land, that crust. And keep in mind, there's a lot of heat, there's a lot of pressure, and these rocks, which are normally solid, can become somewhat molten and plastic, right? When they become molten and plastic, that's when they begin to fold and do things that maybe they wouldn't ordinarily do. So take a look at number two there. With increased pressure from one side, the fold becomes off center, and you begin to see that very dramatically. Then number three, as that lateral pressure continues and increases, the fold becomes even tighter. So it basically doubles back on itself. Let's go to number four. Eventually, the rock layers fracture from all that pressure. They actually break, forming a fault line, okay? And you can see that right here where that fault now has occurred. Those rock layers have actually broken. But as long as that pressure continues to move in from that continent that's colliding with it, let's say Africa, now it begins to slide along that fault zone, forming what we call a thrust fault. That whole landmass is actually thrust up and over, and it slides on top of the other landmass. That slide effect, that sliding can happen over dozens or hundreds of miles. They can be forced to slide on top of another landmass. So in that moment, then you can understand where the layers that were originally flat that became buckled. Now imagine what it might look like to a geologic forensics person, right? You're out there on the ground in Alabama trying to make sense of these layers. So in this case, look at the, I'll actually go to the next slide. Here in this particular case, for example, imagine the knowledge and the expertise you'd have to determine that what you're looking at are actually the undersides of rock layers, where they've actually flipped over entirely, and what used to be their top surface is now their bottom surface, or vice versa, okay? So here, again, I would never be able to walk out there and tell that rock has been folded over, essentially, okay? That instead of looking at the top layer, which you normally would be, you're looking at the underside layer. Here's another way to look at it. Again, you'd have to be a very knowledgeable geologist, trained, to be able to tell that you're looking at an overturned section of rock there. I have no intentions for you to walk out of this classroom and be able to identify those scenarios. But what I do want you to understand is if you're working in the Appalachian region, which is part of what we call a fold belt, F-O-L-D belt, meaning that most of the rock layers have exhibited a lot of folding and faulting, then you should know that then a lot of those rocks may have been highly contorted. Now, in some cases, it's easy to see. Take a look at this. There's a great example of a fold right there. You could pick that out driving 70 miles an hour down the interstate and be like, hey guys, look, there's a fold. Now, notice these horizontal divisions here on the right. Those are the places where the land has broken along those fracture lines and it is being pushed up and over. Those are thrust faults, okay? So that's Africa over here pushing this body of land up and across this body of land here, up and over it in that direction for miles and miles, sometimes dozens of miles. Now, how can we know where these fault lines are? And how do we make sense of all this stuff that's happening, in some cases, miles underneath the ground beneath us? This is where, as your book lays out, they use a seismology. What's this called? A seismic profiling truck. That's what this funny looking truck is here. And they're able then to sort of beam down and look at the structure of the rocks all the way down to the basement layer, the basement granitic layer, which in this case is the Grenville basement rock. Now, what they've done here is, this is a cross section of the Cumberland Plateau up here on the top right. Here's Sand Mountain, Alabama. Here's Lookout Mountain. If any of you have ever been to Little River Canyon National Preserve, that's on Lookout Mountain, or Chattanooga. Then you've got the Coosa River Valley here. And what you can see by using this sort of seismology truck is not only the horizontal layers through here, but you can see the places where these thrust faults occur, right? Notice that. Like say right here, that's a long thrust fault where this slice of land originated over here, right? And it got shoved up and across into its modern position. That's how far these land units have moved. But that seismology truck allows you to detect all these fracture zones, and it allows you to detect any anomalies in the rock. Notice also it can detect when there's an anticline or a syncline. So take a look at Lookout Mountain and let me know, what do you think Lookout Mountain is? Is it an anticline or a syncline? What's that? Anticline for Lookout Mountain? It's dipping down, right? It should be a syncline. Okay, here. So notice these strata are sort of sagging in a concave fashion. So that would be a syncline. Okay, so I just want to show you this. Now, go below the ground. This is a different cross-sectional diagram. And I want you to look at just how highly complicated those rock layers are. Keep in mind, this is at the surface. Here's sea level. Here's 1,000 feet below ground. It's 5,000 feet below ground. We go all the way down to a little over, what is that, 15, almost 16,000 feet below the surface. That's the height of Pikes Peak, Colorado. But yet we're going down underneath the ground. And notice then that some of those rock layers, like the Knox group, which is named for Knoxville, Tennessee, here they're at the surface. That same rock layer is buried in the same location, again, 11,000 feet below ground. The only way that can happen is if that rock had become folded and fractured on itself, pushed down and deeply buried. So what you're looking at here is the bottom half of one of those big folds. Does that make sense? That's the only way you could get that. And then realizing too, that those rocks in that process have been turned upside down, and you're looking at them sort of belly side up. So it gets very complicated underneath the earth, and we should be aware of that complexity. Now, I'm going to show you this diagram here just to kind of help to orient you. This photograph correlates with this diagram at the top. In the far distance, you see Oak Mountain. And then I want you to see here where this house is New Hope Mountain. What you're looking at is basically this house, it's here, and you're looking out toward that mountain in the distance. And across that valley, you can see you're looking out, like at the base of this valley is the Chapultepec Dolomite Formation. But then you've got a fault line. right? Here's Ordovician rock. There's Mississippian rock. There's some shale, and then Mississippian rock there, all the way over to the summit of that ridge. Again, it's very complicated. When we sort of finished up last lecture, we just talked about how much of that rock has been lost to erosion. We don't need to rehash that. I think that's very clear at this point. We've lost thousands of feet of rock above the surface of the ground, as exemplified by the angles in these rocks here. Thousands of feet lost to erosion. Okay, with that, I want to just kind of drive that point home one more time. Now, let's go into our final period of the Paleozoic. We're going to talk about the Permian period. Stretches from roughly 300 to 250 million years ago. And as you can see, we still have Pangaea. We do not have the oceans that we're accustomed to at this point. Remember, we've gotten, we've talked about some of those oceans like the Iapetus Ocean, the Theocraic Ocean. We talked about some confusion we've had with like the Tethys Ocean, for example. We won't spend any more time talking about these ancestral oceans, but what I do want to point out is that very shortly, very soon, we're going to begin to see the first development of the Atlantic Ocean. And you're going to watch for it right here. In fact, this little inland here, actually not that one, probably this, will be the western extension of what will become the Atlantic. So notice the Trans-Pangean Mountains all the way across. We do have glaciers covering the South Pole. And we're going to keep on trucking through the Permian here. Now, I continue to show here the diagram from the publication that showed the mountain building that was involved in the uplift of the Appalachians. And here you can see by this point, everything has come together. All the way from Africa, we've got a variety of different pieces of land. Some of these were islands, like what's called the Carolina or Avalon terrain was an island out in the middle of the ocean. They got jumbled up into North America. That's called a foreign terrain, all right? But that now forms what we now think of as the Piedmont, or a portion of the Piedmont. We also have a separate island that formed the Piedmont terrain. Then we have all these other mountains to the left of that. This right in the zone, that was all the land that was the former basin of the Iapetus Ocean and the Theocraic Ocean that were basically shoved up like a giant bulldozer would push forth a pile of rubble or dirt. Just imagine long before Africa ever got here, those two ocean basins that lie in the middle, they had to go somewhere, right? All the basalt, igneous rock that formed the ocean crust, the rocks that were part of the mid-oceanic ridge, like the gabbro formations, the serpentine rock, which forms adjacent to the mid-oceanic ridge. All that got pushed up a couple of times as those two oceans got squeezed together and all that oceanic crust got deformed and pushed up. And what does it largely form today? The crystalline mountains ecoregion, which is mostly formed from granitic rocks that are either basalt or of rocks that are oftentimes formed very, very deep underneath the earth. So that's kind of where all those mountains come from. So that whole Appalachian building episode really involved lots of different kinds of land units and different processes. Eventually, we get to the far western edge of that, on the western side. That's where we hit things like the Cumberland Plateau and the Interior Plateau, which basically are unaffected by mountain building. They might have been warped slightly upwards to an anticline, or like in the case of Lookout Mountain, they may have experienced a down warping, okay, as a result of that. But by and large, they weren't tilted up. They weren't deformed or metamorphosed. So pretty much everything from the Cumberland Plateau west more or less remains sort of horizontally horizontal without much of a direct impact otherwise. Let me see. I gotta have a little bit more air. Let's see if I can get a little bit of air. James, I don't want to blow you out of here, buddy. So if that gets too much view. How's that? Not too much? I might not be able to take this off. Okay. All right. So now we've got in this Permian period, we have this Trans-Pangean Mountains. It's a hot desert. We've got a massive supercontinent. We've got now, we're about to experience a reversal of plate tectonics. Think about all the things that had to happen for all that's come together, right? That sort of conveyor belt of plate tectonics was pushing things together. Something's about to happen, though, to reverse that, to begin pulling it apart again. And that's what's going to begin to happen toward the close of the Permian period. Okay. All right. I do want to introduce one more little bit about some of these foreign terrains. You know, we talked about a portion of Florida had been brought here because it was part of the crust of Northwest Africa. Here we can see that. If you were to look at a cross section from, say, Birmingham, Alabama, where that one star is, down to about Gainesville, Florida, if you were to draw a cross section down to that line that you see right here, that's what this is at the top, this diagram. So we could take a look here, for example, the area is just north of Birmingham. You can see, because of that seismic profiling truck, we're able to visualize all these fault lines. Okay. We get over here, we've got some lots of thrust faults where various units of land have been pushed over other blocks, right? Here we've got the Grenville Age rocks of the Pine Mountain window exposed. And then all of a sudden, we got this highly altered, totally different rock that forms what's called an apron, okay? It basically is sort of a mantle or a layer that has been pushed up on top of this North American crust. And this rock is that portion which came from Northwest Africa. And we call it the Suwannee terrain. That's the name of it, the Suwannee terrain. Again, a terrain is a piece of foreign land that is sort of pushed onto and accretes, A-C-C-R-E-T-E, means it's sort of appended onto or glued together, if you want to think of it that way. So this Suwannee terrain was brought here and sort of glued onto the North American plate and left there. When they ripped apart again through rifting, this portion stayed behind. Now, here's the African continental crust here, and that's the part which is going to, when rifting begins shortly, that's the part it's gonna, instead of tearing here, as you might expect, it's gonna actually tear here, and this part will rip away again, so that the Atlantic Ocean is gonna form right here to the right of that Suwannee terrain of that apron. Okay. Now, you would never know that you're looking at a foreign terrain if you drove down across northern Florida. Why? Because the surface rocks are all young. But if you were to drill down, let's say through a oil rig platform that is, you know, set up to explore thousands of feet below the surface, that's where you would find this anomalous rock that is actually part of Africa. Okay, so it's a little bit of a foreign terrain, as we call it. Okay. All right. So this is what the land looks like by the late Permian. And with that, we're going to pick up the rest of the story on the next PowerPoint, because that's really not all to the Permian. But I decided to add a couple more slides. And rather than go back in and alter that particular PowerPoint and have to upload those again, I just decided to add it to the next lecture. So let's open up now the Mesozoic, and let's look at what begins to happen at the very close of the Permian. Well, the very close of the Permian was not a time when any of us would have wanted to exist. Thankfully, no people existed back then. But this is when we see the Permian extinction. This is one of the largest, this was the largest mass extinction in Earth history. There's a link here which I provided in this. And by the way, this version of the PowerPoint is now uploaded on D2L. If you just simply go to the Mesozoic, as of late last night, I think this one's up now. But this link will take you to an article that some MIT professors wrote about this. And there's some emerging data that suggests that this extinction, which wiped out 96% of all marine species, 70% of all life on land, happened in less than 60,000 years during the end of the Permian period. Now, that's really why we mark the end of a period anyway, more or less, is that usually at the end of a period accompanies some major transformative event. That's how geologists sort of decide to delineate one period from another. So that's the thing that marks the end of the Permian, is this massive extinction event. So I would encourage you to check that article out. It happened about 252 million years ago. The consensus is that most of this life on land and in the water was simply poisoned to death through a massive long-going volcanic explosions lasting tens of thousands of years. These are in what we call the Siberian traps in Siberia, part of Russia. These volcanic episodes were happening over tens of thousands of years, spewing sulfuric acid and nitric acid, all kinds of toxins into the atmosphere. And of course, the water, not only was air undergoing pollution, but it created a toxic soup in the water environments as well. So this does obviously, indicates the possibilities for us to, again, lose major chunks of our biodiversity to global extinction events. I think the one silver lining here is that you can't prevent these things, right? And that after the Permian extinction, in which case a lot of amphibian groups went extinct, probably some early reptilian groups would have gone extinct. We probably would have seen the extinction of many different fish lineages. But think about what we didn't have yet. Think about what's yet to come. All the flowering plants, they had not evolved by this point. Mammals had not yet evolved. Dinosaurs had not yet evolved. Birds had not yet evolved. Most insect groups had not yet evolved. So when you have these major mass extinction events, it's like a reset. And yes, it takes obviously millions, tens of millions of years to recover, but life eventually does recover. So if there's any silver lining to the screw ups that humans are doing to this planet right now, we can all rest assured we are guaranteed to go extinct as a species. That's not even up for debate. I mean, the evolutionary record proves it, that every species on Earth will go extinct. It's only a matter of time. And when we do, and so will these other majorly successful species eventually, cockroaches and Norway rats and fleas and the other really successful critters, they also will one day meet their doom. But with all the havoc that we've wreaked on this planet and all the good we've done too, it will one day come to an end. And when it does, the Earth will go through a long period of resetting itself, and evolution will begin again. It always is going. So the Permian mass extinction was a huge deal. And at the end of that, we now enter a new period. In fact, we're going to enter a new era. It was such a massive reset to life on Earth that the life that comes next, because we almost wiped out the entire realm of biodiversity, what comes next is so different. It's a whole turnover of life. Instead of being dominated by a watery world where fish and amphibians and spore-bearing plants dominated the Paleozoic, things like mosses and ferns and their relatives, we now go to a time on Earth when the things that were able to succeed through these very hard times were things that had seeds and things that laid hard eggs, right? Those were the most successful groups. Not always. I mean, things like insects too. So we're going to see reptiles are going to really flourish in the Triassic. We're going to see the flourishing of many different kinds of plant groups and insect groups as well. All right, so let's take a look at this chart one more time, just to kind of reacquaint ourselves. With the Triassic period, we have a couple of firsts that we should take note of. We have dinosaurs for the first time ever. Now, remember, reptiles originated during the previous, actually two periods before. We get reptiles back in the Pennsylvanian. They undergo a radiation. Y'all know that term, right? Radiation, evolutionary term, which means that reptiles massively diversified during the Permian. But the actual first dinosaurs don't come into being until the Triassic. Now, when I was in school, we thought mammals didn't come along until the Jurassic. That now has been pushed farther back due to recent mammal fossil discoveries. So we now know that mammals actually evolved at least by the late Triassic period. They were small, shrew-like animals that evolved out of the reptiles. Okay, so the Triassic period, 252 to 201 million years ago. And one of the things that you notice by this point in time is the reversal of plate tectonics is now beginning to be evident. Notice that North America and future Africa and future South America are about to part ways. And it's going to happen here because all of a sudden, these new mid-oceanic ridge complexes or mid-oceanic ridge systems are going to begin to develop over these hot spots. That's going to begin to tear the continent apart and form what are called rift valleys or rift basins. So we have Triassic rift basins here, which is then a place that's it's very low, these valleys, and they collect water. Some of them are receiving water from the adjacent oceans that are flooding in as well. Okay. Couple major things geologically speaking. Number one, part of the reason why we don't have any Permian rock and we don't have any Triassic and Jurassic and early Cretaceous rock is it was a time of major uplift during that whole time period. The area over what is now the Southeast was becoming rapidly uplifted. It was a mountainous region, okay? We didn't have any depositional environments really right here over Tennessee, Kentucky. So this was a substantial period of uplift of the North American craton that began in the late Paleozoic and continues all the way through the late Mesozoic. Secondly, we can quantify how much rock we lost during that time period. 1,500 meters of sediment and rock was eroded just from the interior plateaus and the central interior lowlands. So that would be like over Middle Tennessee and Kentucky, Indiana and Illinois, parts of Missouri. We're looking at 1,500 meters of rock. How many feet is that? Approximately 4,500 feet, more or less, okay? That has eroded. Now think about that. That's roughly how high the Great Smoky Mountains are from the valley bottoms, let's say the elevation of Knoxville, to the top of the Great Smoky Mountains. Because Knoxville's already at about 1,000 feet. So up to the top of the Smokies is about 5,000 feet gain, up to 6,000. So you're losing roughly everything in the Smokies over Clarksville, over Carbondale, Illinois, right? Over Louisville, Kentucky. We've lost that much rock. And that's why we don't have any fossils from that time period. That's why we have a big unconformity and it's missing. Okay, so Pangea is about to start splitting up. We can see that through these rift valleys that are occurring, and they're occurring along multiple seams. We have one rift that's happening here between Africa and North America. We have another rift that's going to be here later between Africa and South America. And then we have a third one here between southwestern North America and northern South America. There's a lot of heat involved in this process. There's a lot of lava that is just basically pouring out, forming these massive lava flows. Along with that heat and the fact that it's already a desert is making it even hotter, okay? So we're in still very much desert-like conditions. Here are these Triassic rift basins. And if you want to know what these look like, these were hot, sterile environments, very much like you might picture parts of the Atacama Desert of South America. Or maybe better yet, the Olduvai River Gorge, the Olduvai Gorge of Eastern Africa in Ethiopia, and parts of maybe Eastern Ethiopia, Kenya, and that region. Notice that if the rocks at this time would probably have been very red, very much like parts of New Mexico or Arizona. You would have had what we call playa lakes. These are temporary lakes that come in the rainy season, which you often have in desert regions. You might get a couple inches of rainfall. You may have a playa lake that's only a few inches deep at best. Very salty water. Think about Great Salt Lake, Utah. That's what a playa lake would be, okay? And many of these were not that big. Some of them were much smaller. You would have had earth flows of rock and gravel and these alluvial fan deposits where landslides would carry those rocks down, contributing to the erosion. Again, very hot environment. A lot of evaporations happen, okay? You're going to have a lot of salty, a lot of salts that are going to be forming crystals and being left because the moisture is being sucked out of the air through evaporation. Now, how do we know what this region of the country was like during the Triassic period if we don't have any Triassic rocks in Tennessee or North Alabama anymore? Well, we can go to two nearby sources. Number one, we can go to South Alabama and Florida, southern Georgia, and we can use oil and gas exploration rigs, which they drill down. They take a core that's about 3 inches in diameter and drill down looking for oil and natural gas deposits. And here's an example of what one of those looks like. This is about 3 inches wide. It's solid rock, right? So this is not sand that you're getting back up. This is a solid rock core. But I want you to notice that it's red sandstone. It's very red, just like we would expect, parts of Sedona, New Mexico, or Sedona, Arizona, I guess. And then notice this unevenness with respect to what's called cross bedding. If you were to go to the beach or to a sand dune in the middle of a desert and dig down into its face and look at it in cross section, you would see that those sand dunes have been blown. Like, imagine if the winds are blowing from the west. They'll blow a dune up, and that dune will be sloping, right? What happens if the winds shift from the east? Then all of a sudden, the dune begins to blow back in the other direction. So you get cross bedding. That's what we're seeing right here. The evidence of that dune formation is very visible in those cross beds. So this is a particular section of rock that is underneath the area about where Mobile, Alabama is, if you're sort of following me geographically. And this is about 3 miles below the modern surface. That's how deep you got to go to get to this particular formation called the Norfleet Formation. But let's see where it is in relation to all the other rock that they had to drill down through. So that's over here on the left. And you can see up at the surface when they started, right? They're in Holocene, the Holocene epoch. You go back to the Pleistocene, then the Pliocene. We hit the Miocene, multiple different layers. Notice how they're all shifting, right? You're going from sand and gravel and clay. Then you hit a clay from the Miocene, then a fine-grained sand, and another clay. There's all this sort of overlap and repetition. Finally, we get back, and we don't have a depth chart here, I don't think. We go through a little layer of the Oligocene that's limestone. We hit the Eocene, and the Paleocene. At this point, we're probably, if we're on our way down to the Triassic, right here, if this is 3 miles deep, you can probably get an idea for how deep you are here, roughly a mile or so. And we keep going through the Eocene, Paleocene, the Upper Cretaceous, the Lower Cretaceous, Upper Jurassic, the Middle Triassic. Finally, we get all the way down to this formation. Now, this one right here, it's actually Upper Jurassic, Norphlet Formation, sandstone from about 140 million years ago. It's 3 miles below the surface. And it has all the signatures of being a desert at that time. Now we can go a little bit to the east of Alabama and Tennessee into what are called those Triassic Rift Basins. Actually, one of the ecoregions for the Piedmont is called the Triassic Rift Basin ecoregion. These are these sort of valleys that are filled with Triassic bedrock. So like right here, just outside Raleigh, North Carolina, or up here east of Richmond, Virginia, are Triassic basins that are filled underneath the soil layer is Triassic bedrock. If we were to look at those rocks, then we can see that they are bright red. They have all the signatures of things like landslides, and there's conglomeratic boulders with some rounded cobblestones. These are red type sediments like you see in desert regions. But the real clincher that this is a desert region beyond those that I mentioned is the presence of a mineral called anhydrite. Okay. This mineral shown here, which can be anything from a sort of a reddish color all the way to a pure white, these are minerals that are evaporite minerals. They are caused specifically when salty water evaporates under hot temperatures, leaving behind these crystals, of which there are several types, but this one particular kind is called anhydrite. Now, here's how you expect those to form. These are basically what we see associated with salt flats, like in Nevada, or here's the Atacama Desert of Chile. And this is an area where if you have like in these Triassic Rift Basins, it's separated from the ocean. The ocean proper is off over here to the east. We have this basin that is filled with this playa lake that's very seasonal, subject to desert rainfall. And then as those temperatures are heated up, a lot of that water evaporates, leaving those salt crystals sort of at the surface. Once that's the depositional environment, right? Is this basin. If those become covered up, let's say by alluvial sediments or by adjacent landslides, then those get preserved in the rock record. Those get preserved in the geologic record. And those evaporites tell us something very specific, that it was a desert basin with salt flats. And so that's part of the story of this region as recorded in these rocks of this area. Now, some of the fauna that would have existed at that time, these are some artist renderings from Germany and Switzerland from the same type of age. We had very small dinosaurs at this period. Some of them were a little bit larger than a human. A number of things like turtles and various types of lizards were certainly already established by that point. As far as plants go, one group that really succeeded were the seed plants, particularly a group known as cycads. And most of you probably have seen a cycad, especially if you've gone to a tropical region or if you've gone to a botanical garden where they have some indoor plants. So cycads sort of look like a palm tree that has this sort of pine cone thing off the top of it. And I know, like in James's case, it's taken Dr. Lebketcher for botanical diversity. You get to cycads when you start talking about gymnosperms and the seed plants, the conifers, because the cycads are an example of one of the gymnosperm groups. But there's another sort of common term sometimes applied to the cycads, and that is dinosaur plants. It's thought that the cycads were one of the major food sources for many groups of dinosaurs. Here you can see an artist's rendering of a Triceratops browsing on a cycad shrub. Not all of them were tree size, some of them are shrubby. Here's another larger type of sauropod dinosaur eating from a cycad that's more of a tree. And yet another artist rendering showing a few cycads in addition to other kinds of plants. So we have some trees here, like which are more of the needle-bearing trees called like monkey puzzle trees. Today, they're primarily found in New Zealand and South America, Australia. But then we have cycads here. We've got some ferns. This is a cycad as well, probably. We have a ginkgo, it looks like here. And we've got some horsetails, things that were somehow able to survive the Permian extinction. But many of those big trees that form those vast coal swamps, they're all gone now. They've all gone extinct. Some of their smaller forms have persisted. Now, by the middle Jurassic, roughly 201 to 145 million years is the whole period. So during the middle of that period, we begin to see this rifting is taking effect. Notice now that the young Gulf of Mexico is really beginning to open up. Okay, that's primarily between, here's Venezuela here, and here's northern Mexico and South Texas. So that's where the Gulf of Mexico is opening. But keep a watch on the Mississippi embayment. That's that region that is the lowland along the lower Mississippi River Valley. Why do you think the Mississippi embayment is forming right there in that particular location? Go back and think to a couple of weeks ago or last week. What did we talk about? Failed rift? Exactly. Were you going to say that same thing, Chase? Yeah. The fact that we had a failed rift here that goes all the way back deep into the early Paleozoic means that this was structurally already a fragile place, right? It already was fragile, and it was already naturally an area that had sort of a down warp to it, even after going through Pangaea's formation. And now Pangaea's breakup, that area still has a swag to it. And because of that, that's going to play a major role in the formation of the Gulf of Mexico and in the formation of the lower Mississippi River Valley, even through all of that geologic change and upheaval. Matthew?
This map, a bunch of rivers are starting to form.
Yeah.
Those the ancestors of rivers have
Great question. Super great question. I think these are all just conjecture. I don't think there's any way possible of knowing where these rivers were at this time period, because keep in mind, it was about 4,000 or 5,000 feet above where we are today. And we don't really have any way of knowing where, with concrete evidence, where the rivers were. So for those of you online, Matthew was asking about, if you look here on this map, you'll see these rivers are indicated. And he was asking, you know, are those the ancestors to modern rivers? And I think the answer there is no, that this is purely artist rendering, trying to provide a little bit of guesswork. We're going to need to go all the way. So from roughly 175, 180 million years, we need to come all the way up to about 20 million years ago before we can really conclusively start predicting where paleo rivers were located. And that'll be part of Thursday's discussion. Great question. Any questions before we get ready to leave the Jurassic period? Anybody online have a question?
Good to go.
Good to go. All right. Can you guys see how North America is taking shape? It's pretty wild. Now, notice off, to the West Coast, there's a lot of stuff that still has to happen, right? The whole western seashore of Washington State and California is a long way from being formed. That's part of our discussion we'll have on Thursday. But notice that, here's the eastern edge of Nevada, but like the entire regions of Washington, Oregon, and California aren't even here yet. And the building of those is going to be an important part of our story. We will talk pretty substantially about what happens on the West Coast, because it will have a dramatic effect on us here in the Eastern United States. Okay, so by the time we get to the Jurassic, again, dinosaurs now not only have evolved, because that was in the Triassic, but now dinosaurs are flourishing, they're radiating, they are undergoing diversification. They are filling the air, the land, and the sea. We have all different kinds of dinosaur groups at this point. One particular group of dinosaurs called the theropod dinosaurs, those are the descendants of things like Tyrannosaurus Rex and some of their cousins, like those little dinosaurs with those little small, like forelimbs, right? Those dinosaurs will go on eventually to form into birds and give us the lineage that today is birds. Birds are nothing more than dinosaurs with feathers. So we do still have living dinosaurs on Earth, but they just happen to be in the form of birds. Now, notice there's one correction we probably need to make here. Notice that on this diagram, it says first flowering plants come at the end of the at the beginning of the Cretaceous period. That actually has been pushed back now. Flowering plants, what we call anthophytes, angiosperms, they now have been shown to have definitely evolved in the Jurassic period. Sort of how we're pushing mammals back farther, we're now pushing flowering plants back as well. Okay. So a big focus now is on what's happening to the Atlantic Ocean. Notice just between 230 million years ago and 150 million years ago, so just an 80 million year span of time. And notice how much the Atlantic has opened up between the middle Triassic and the late Jurassic on the right, okay? Hundreds of miles of ocean has opened. Keep in mind, we said that that rate is roughly the equivalent of how fast your fingernails grow. That's how fast the continents are moving apart. What's driving, let me ask it to you as a question. What's driving the separation of those continents one more time? Seafloor spreading. And in the middle of that seafloor, you would expect a mid-oceanic ridge, right? And it's exactly what we see. If we were to, have y'all ever seen those shows on, like, I don't know, Discovery Channel or National Geographic, Drain the Earth, Drain the Oceans, right? And Drain the Great Lakes. It's all about what would happen if you drained all the water away and looked at the floor of the ocean. What would you see? If you drain the North Atlantic Ocean, and here you can see North America on the left, here's Spain and Europe, there's England, Ireland, here's Africa, there's South America. Here you can see the mid-oceanic ridge going all the way up. It's got a bit of a zigzag here. It's going to go up and go right to the middle of Iceland. So that mid-oceanic ridge is a really prominent feature on the floor of the Atlantic Ocean. It's in the middle of all the major ocean basins of the world. But what's more is we can tie the timing of the rocks that form the mid-oceanic ridge and the floor of the ocean on both sides. We can specifically date those rocks using various rock dating techniques, radiometric dating. So let me ask you this. What would you expect, roughly, the rocks at the ocean ridge to be? How old? How old are the rocks at the mid-oceanic ridge? So pretty fresh, right? Give me some idea of, millions of years. It could be from yesterday old, right? To maybe less than a million, right? It could be a few million, right? And still be somewhat close to the ridge. How about, let's go back to the west here. How about right in this zone, in sort of the middle of the deepest part of the Atlantic Ocean basin to the west of the mid-oceanic ridge? How old is that rock? How much? 130, says Kian. Okay. By the way, what kind of rock forms the crust of the ocean basin? It's basalt. Good. Well, we've come a long way for not really being a bunch of geologists, right? Playing some geologists in the movies. You see how y'all said that all in unison? That was nice. All right, so we can actually date these rocks. Where would the oldest rocks be before I proceed to the next slide? Where at, Ryan? Farthest away, right? Up against the North American continent. That's exactly what we see. Here, you can see roughly, 10 million years almost, all the way down to about 180 million years. The bright red, actually the black zones are the most recent and progressively gets older and older and older as you move out. Notice the Gulf of Mexico and right along the western edge of America. Those are the oldest sections. And by this, it looks to be around 160 to 180 million years. Let's go back real quick and let's take a look at this and see if that comports with the geologic maps. Here's 150 million years, right? There's 230. So this right here makes sense to be about 180 million years. That makes sense. Now, the last thing I want to highlight here, and then we're going to take a break and we're going to come back and focus on the Cretaceous period for the second hour. During this time is when we begin to see, I'm just going to mention them here because they're kind of like anomalies. They're just sort of cool to talk about. But this is the, remember we talked about the Wells Creek structure, the meteor impact that's just southwest of Clarksville? It's thought that that happened during the Jurassic period, roughly 200 million years ago. You drive right through it. In fact, when you go to the town of Cumberland City and the town of Erin, there's Cumberland City right there, just about 20 miles or so to the southwest of Clarksville. There's a little restaurant right here in the town of Erin at the bottom of this slope. It's like a hot dog and burger joint. And anyways, you can, as you're going through the drive-through, and I've been through it a few times, as you can see, as you're going through the drive-through, I always look up and appreciate how complex the rocks are in that adjacent slope. Because to someone who knows what they're looking at, that's a very unusual scene for Middle Tennessee. Most Middle Tennessee hillsides that are cut away should have very regular flat-lying sedimentary rock. Here, you've got cracks and fractures and everything's jumbled and tossed and turned. And if you really know what you're looking for, you might even find what are called shatter cones. That's where the heat and force of the rock was so powerful and intense that it actually melted the ejecta, the rock debris that was flying out. It melted it instantaneously into glass. And that's one of the signature things that people look for who study these kinds of meteor impacts. Here's what you see, that bit of shocked glass there, shocked quartz. By the way, this is a separate meteor impacts site down near Alabama. This is just north of Montgomery, called the Wetumpka astrobleem. And astrobleem is just another fancy word for a meteor impact structure. Okay. This is what Wetumpka looks like from the side. Highly distorted beds, all in Cretaceous gravel. So this actually is a little bit younger. This probably did not happen in Jurassic. It actually happens in the early Cretaceous. You can see the rocks have been highly deformed that are cropping out on the edge of the rim of this meteor impact here along the Coosa River. And with that, let's take a 10-minute break. We'll come back at 5:55, and we'll spend the next hour talking about the Cretaceous period. Okay, gang. So we're now ready for the Cretaceous period. Okay, so without further ado, let's jump in on it. Cretaceous period. This will be the last period of the Mesozoic era. There's only three, right? Triassic, Jurassic, and Cretaceous. So we're talking about a whole time span of 145 to 66 million years. I'm showing you here the differences in North American geography. By the way, we formally have North America at this point, okay? Everything really before the collision with Pangea, we called this landmass something else, like Euramerica or Laurentia. Now we actually have North America for the first time. So compare the early Cretaceous North American landscape to that of the late Cretaceous. There's a few key things. Let's point out what's missing right now. Or let's point out what's present. Number one, by the time we get into the late Cretaceous, we have a continental seaway, what's called an intercontinental seaway, that is fully dividing North America into an eastern and western section. This seaway would have covered most of what we think of today as the Great Plains. In fact, the Great Plains will develop largely because of that seaway is there. And there's lots of course, marine fossils from this region of Kansas and eastern Montana, things like plesiosaur fossils and shark fossils and all that kind of stuff. Clayton?
That seaway standing or is there a directional current?
Oh, I'm sure there's a current. Yeah, I mean, it's a shallow seaway, but in places it's probably a couple hundred feet deep. It's definitely deep enough to support mosasaurs and plesiosaurs and large aquatic reptiles.
I had a question.
Yes.
Is that seaway there long enough to put down limestone layers?
Oh yeah, absolutely.
Okay.
Yeah, this seaway is there for. I mean, if you look here, for example, over eastern Montana and the Dakotas, I mean, it's there at 115 million years. It's still there at 85 million years. That's a lot of time, to lay down some limestone. And
Okay.
we'll talk about what happens to that seaway. Why does it disappear, for example? We do have at this point, of course, the Rocky Mountains are still the Appalachian Mountains here on the east are quite high. They are rapidly sort of being diminished. They're rapidly being eroded down. You do have sort of various precursors to the Rocky Mountains out on the West Coast. It's a very rocky environment, but you do not have things like the Sierra Nevada mountains yet. You do not have the coast mountains, for example, along the coast of California. Those will all come much later. The modern day Rockies, it's thought that many of these western mountain ranges that you see here will kind of erode down, and then it's not that they go away, because this part of the western part of the continent is rapidly being impacted by continual mountain building. And so the modern day Rockies we kind of think of as sort of originating probably like in the 60 million year window up until the more recent times. Take a look at the coastline of the Southeast and we talk about the coastal plain physiographic province or region. So pretty much the way we delineate that is everything that is below the coastline as of the late Cretaceous. That was the difference between being on the continental shelf, right, out in shallow water on the continental shelf of the ocean, to being on land. It was a pretty dramatic step off from land onto the continental shelf. Over the next 85 million years from this image on the right, we're going to see the continual recession of that coastline. That's going to sort of predominate what we'll talk about during the Paleogene and Neogene periods. Basically, that coastline is going to continually move to the south all the way until about 2 million years ago, until it gets to its modern position. But when we say coastal plain, basically we mean everything that was sort of covered by ocean up until roughly 65 million years ago. Okay. Another thing I want to kind of point out is it's not immediately obvious here, and I'm just going to hit the highlights on it. But take a look on the left side of this image at 115 million years. What's missing south and east of Florida? Yeah, or south of Florida in general. Yeah, we're missing Cuba, and we're missing what else? Puerto Rico and the island of Hispaniola, right? Haiti and the Dominican Republic. We're missing all those Caribbean islands. Jamaica is missing. Where are they at 115 million years ago? Where's that? They're not necessarily underwater. They're in a different ocean. I know. It's pretty cool. Cuba and Hispaniola, Jamaica and Puerto Rico were in the Pacific Ocean before they came to the Atlantic Ocean. You see, they're on their own they're on their own continental plate called the Caribbean plate. And that plate started out a few tens of million years earlier than this image by being located approximately north of the Galapagos Islands. Cuba was an island and these other islands were there. Some of the small ones like Martinique and Barbados are all pretty young. They developed later from volcanic activity. But the bigger islands like Cuba, what we call the Greater Antilles, they were in the Central Pacific Ocean. And Central America and Mexico at that time did not exist. It was an intercontinental seaway, right? After South America begins to pull apart, an ocean begins to spread through between North and South America for the first time. As that happens, as those two continents split apart, these islands that were Cuba, they began to move through that divide into the modern position of the Caribbean Sea. You can see them coming right here. You see that? In fact, they're coming with their own tectonic plate boundary, a subduction zone. And as they're moving to the northeast, what's happening right along that subduction zone? Oceanic crust is doing what? Going down. Actually, it's the other way around. Excuse me. The continental crust, or this crust, is lighter than oceanic crust. It's less dense. Therefore, it is subducting underneath oceanic crust. That's leading to a hot spot that's creating a volcanic island arc. And that's why we have the islands of Martinique and Trinidad and Tobago and the Virgin Islands and Barbados. Many of them are volcanic that form the Lesser Antilles. And if you look, they form an arc, similar to how Hawaii and some other volcanic island arc chains have formed. So anyways, just know that that's going on in the Caribbean region down to our south. Now, between 115 million years ago and 85 million years ago, take a look at Mississippi and West Tennessee and Alabama. You can see the remnants of that failed Rift Valley right here, that projection northward of the ocean into what's called the Mississippi embayment. Now, that's really important because that's a structural weak point in the North American continent. All right, and with that structural weak point, the strata of rock are naturally down warping. They're bending down, and this down warping on the edge of the continent leads to the Gulf of Mexico, extending northward, forming what's called the Mississippi embayment. This is that lowland region along the lower Mississippi River Valley. That embayment, as it sort of bows down, is receiving the sediments that are washing into it from all around, from the surrounding uplands. And so that's why this area, it's thick, really thick with sediments right here above all those old Paleozoic rocks that are buried underneath it. There's thousands and thousands of feet of sediment washed into that. Think about that though. All that sediment washing in, piling up above those old, already very deep layers of bedrock, adds even more weight to that area, to a structurally weak area. More weight means more down warping, okay? If land is down warping in one spot, what might it be doing immediately adjacent to it? Uplifting, right? That uplift and the adjacent down warping is what's driving things like erosion rates. So with the down warping of the Mississippi embayment, the surrounding uplands are uplifting, eroding faster, and those sediments are eroding down into the Mississippi embayment. And guess where else they're going? Onto the new continental shelf, which is now underwater in this whole region right here. And that's not just happening along the Mississippi embayment, right? There are rivers which aren't drawn that are going all down off these mountains, flowing onto the continental shelf and emptying their sediments up depositing layer after layer of new sedimentary rock materials. That's the depositional basin, depositional environment. Not only is there limestone being formed, right? But because of the influx of new sediments, you're getting sand, which is forming sandstone, and silt, forming siltstone. So that's contributing to the rock formations that will eventually make up what's called the coastal plain today. Now, let me ask you a question. Where would you expect fossils in this region of, say, Tennessee, Alabama, Mississippi? Where would you expect fossils from the late Cretaceous period? What two types of environments would you expect fossils? Marine fossils, let's start there, okay? Yeah, marine. You would expect in those shallow oceans that the limestone layers that have been laid down. Who said limestone? Somebody on here? Maybe Laura said it. So we would expect in those limestone layers or chalk layers, which is similar to limestone, that we ought to be able to find a variety of marine organisms. And that's exactly what we see when we go to places like Mississippi or here in Alabama along the Tombigbee River, extensive chalk deposits. By the way, keep in mind those chalk formations are themselves the fossilized remains of protists that are called coccoliths. God, that's a hard word to say with a southern accent. Those are the fossilized remains. If you go back to our original PowerPoint presentation on geology and look at them in a highly magnified view, those are made up of coccolith deposits. But inside these bluffs, we can find things like mosasaurs. These are like, 50-foot long swimming reptiles. They're not technically dinosaurs, but they're sort of cousins to dinosaurs. Here's some ecologists or some paleontologists from Alabama. And you can see they are out on a field day excavating a mosasaur fossil. Here's a section of the jawbone on the right. And that's in a chalk deposit that's in a former prairie landscape. Also, some very large fish. These are on display at the McWane Museum, McWane Science Center Museum in Birmingham. And giant extinct marine turtles, some of them almost 10 feet across. Lots of oyster fossils like the genus Exogyra. By the way, these are found also in the Cretaceous marine deposits in West Tennessee. There's a few places down in McNairy County, far up into like Henderson County. There's a specific geologic formation called the Coon Creek Formation. It's very rich in these particular Exogyra fossils. Another Exogyra here in the face of this bluff of the Tombigbee River. Here's a crab shell. That's pretty cool, right? This is in a deposit in the Black Belt ecoregion of Alabama. Lots of shark teeth. Anybody who knows what they're doing, it's not me, but you can go out here with the seine and you can find hundreds of shark teeth easily in just a few hours' time in these gravelly, chalky riverbeds. Even coprolites, the fossilized poop remains of possibly either sharks or mosasaurs or fish. These are fossilized poop. And the vertebrae of many different kinds of fossil fish are found in these deposits. Also plesiosaurs, Loch Ness Monster comes to mind, right? Here's the giant vertebrae of the plesiosaurs on display at the McWane Science Center. Okay, now those are for some marine fossils from the Cretaceous. And the reason we know that, right, is because by the time we get to the late Cretaceous, we have those rocks preserved in two different depositional environments. In the marine deposits, and then we have terrestrial deposits, right? Not in the ocean. And where would you expect those? Where would you find terrestrial Cretaceous rocks with fossils of terrestrial species. Swampy, marshy, river floodplains, low coastal areas, right? They have to be low. If they were up high, they got eroded away a long time ago. So if we go to areas like down around Montgomery, Alabama, or just over the line, over across the Tennessee River into West Tennessee. Remember, Tennessee has a single dinosaur fossil ever, and it's one bone from one individual of a hadrosaur, one of the duck-billed dinosaurs. Where was that found? Right there in that little sliver of brown, right there that kind of hangs down. The farthest little sliver right to the left of my finger. That's where Tennessee's only dinosaurs ever been found. If we go down in Alabama, though, they have a much richer array of Cretaceous fossils. And lots of those fossils, you know, some of them are in these kind of gravel beds of Cretaceous rocks. So, for example, if you look up close at these rocks, they look like pea gravel, like you might go buy at Home Depot or Lowe's. You can buy a sack of pea gravel or get a load of it in your truck. Very water-worn, very white gravel beds, oftentimes intermixed with coarse sand. And this is where you had rivers and streams that were kind of going in and out of the oceans right there along the coastline. Here's some of those same gravel deposits and sand beds of the Cretaceous Formation. And this is one of the fossils that is found there. It's not a very good image, so I'll kind of show you another. Fossilized tree trunks. So this is lignitized wood. If you were to touch this, it actually looks and feels like real wood. It looks like mummified wood in some cases. Sometimes it's still so fresh that it would even burn. In other times, it's been replaced with silica crystals and hardened into stone. And I'll show you some of that in a minute. There's also things like nuts and various cones of various types of trees that are also preserved in some of these formations. Here's a section of Paraphyllanthozylon, which is a formed fossil for one of these particular types of trees. These are very common in Mississippi and Alabama in some of their streams. This is Uhoppy Creek in Macon County, Alabama, where this particular specimen was documented. Here's a section of brilliant wood, as it's called, which has been silicified, where the minerals of the wood, or excuse me, the cells of the wood have been replaced with silica crystals. So it's basically turned to stone. And you can see the quartz crystals there. But we also have preserved remains of fossil leaves. Some of these, almost all of these, I should say, with a couple of exceptions, do not grow around here today. The one exception is the water lotus up in the upper right. Have you ever seen a water lily kind of maybe sticking out of a marsh or a pond around here? That's the same genus that we still have today, the genus Nelumbo. But then these other ones, like the genus Cinnamomum, is a tropical relative of the sassafras tree. Aurochites is a type of conifer. And then Phyllotes is a type of tropical fig. In most of these cases, these all indicate that this area was tropical rainforest or subtropical forest at the end of the Cretaceous period. So there's been a lot of work in West Tennessee and Alabama and Mississippi to study the fossilized remains of what we call Cretaceous floras, studying the plants of these areas. Most of those indicate that those plants are today similar. They're either totally extinct or their relatives are in the tropical rainforest of what region? Where would you think the closest relatives of these tropical species would be to the southeastern part of North America? In South America, you would think, right? Because
Africa.
maybe Africa. Any other guesses? You would think that South America would make the most sense because it's geographically the closest, right? But keep in mind that as the Jurassic started to happen, South America pulled apart from North America. Its forests became isolated for the rest of all time, all the way until 3 million years ago. So at the time that these species were living in this region, the connectivity was not to the south, of South America. It was actually through Alaska and through Greenland, through Europe and Asia. And so these species actually bear their most close relationships with species that we see today in Southeast tropical Asia, in places like Indonesia, Malaysia, Cambodia, Vietnam. That's where most of these species have their cousins. We'll talk about why that is later. That's a whole fun story unto itself. We have terrestrial birds and seabirds, as you might expect, that are sort of close to the shoreline. Here's the bones from a pelvis of a Cretaceous bird. And of course, we have still dinosaurs, but not for long. Notice this is at 70 million years ago. We're going to lose them in 5.5 million years, right? At 65.5 million years, dinosaurs are going to go extinct. Some of those dinosaurs are pretty interesting. Here's one. This is a relative of Tyrannosaurus Rex that was found on the grounds of the Alabama State Capitol building while they were doing some renovations. And right there, immediately outside the Capitol, you can see there is where they found the complete skeleton of a new genus of dinosaurs called Appalachiosaurus montgomeryensis, since it's found in the city of Montgomery, Alabama. Now on display at the McWane Science Center in Birmingham. But let's not forget, we did have some mammals as well, and some mammal-like reptiles at this time. Here's some little mammals kind of hiding down, snuggling down in the leaves over here, just waiting for their moment, right? Just wait, little mammals, 5 million more years. You'll finally get your day to dominate the planet. And of course, we have birds as well at this point. You can see some of those in the background. Then at 65.5 million years, one day, something very unexpected happened. We have a massive asteroid that collided with Earth and landed off the coast of modern-day Yucatan, Mexico. Now, for the longest time, scientists didn't know this. There was no substantial proof of this that they could find yet. They gradually began to suspect something massive and catastrophic, like a meteor impact or an asteroid impact. But it was only after quite a bit of detective work that they began to really settle on that being the leading cause for the extinction of the dinosaurs. Once they had a very strong case that it indeed was a meteor or asteroid, I don't know the difference between the two, to be honest with you. What's the difference, Chase? So hell, it's all the same, basically, right?
Meteor and asteroid different size.
Oh, okay. All right. Okay. Basically, what I'm going to keep calling it one or the other. I may use them interchangeably. All right. Space rock. Okay. Because one of the many classes I never had was an astronomy course, right? I do not play an astronomist when I'm asked to in the movies because I don't know a damn thing about astrophysics and astronomy. All right, but let's get back on topic. Yeah, what's the Chat GPT say?
The difference between a meteor and
Okay, I think Chase. All right, so asteroid when it's in space, meteor when it's in the atmosphere, meteoroid when it makes impact. Meteorite, got it. All right, that sounds good. Thank you, Chase. That was very illuminating. All right, asteroid in space, meteor when it's in the atmosphere, meteorite when it makes contact with the Earth, right? Okay,
Very
cool.
illuminating, you said.
Very illuminating, yes.
Pardon the pun.
Pardon the pun, yeah. So for a long time, for a few decades, scientists suspected, based on a wealth of evidence, that it was a meteor strike that had led to the demise of the dinosaurs. They did not know where the strike happened. And that's really part of the cool aspects of the story we're going to get into. So yes, very illuminating, right? Very bright. This was sudden. This was almost like, just boom, swift. Now, did all the dinosaurs die instantaneously? No. but many who were, geographically within the span of probably, 1,000 miles or so, probably would have died almost like the impact of like a nuclear bomb, right? Just the waves, the shock effect would have been tremendous. The heat that would have encircled the earth would have been tremendous. Some dinosaurs, and of course, then all the debris, the rock and the ejecta, the dust and debris that went into the atmosphere would have been tremendous. It would have been enough to block the sun. And for warm-blooded animals like dinosaurs, it definitely could have put us into sort of an apocalyptic scene that what do they call that? It's like an asteroid winter. Is that what they call that? There's a word that's connected with something like something winter. Yeah, similar to that, right? Yeah. But it's triggered by things like a meteor impact that causes us to go into much cooler conditions that's below the threshold that most dinosaurs could survive. Now, let's talk about what was some of the original evidence that paleontologists and geologists were finding, which led them to suspect an asteroid in the first place. Well, number one, there's, let's see, right here. Number one, it was the multiple independent observations from many, many different places all over Earth. China, Mongolia, South America, Europe, North America, where never in the history of paleontology had people discovered fossils of dinosaurs in sediments younger than the Cretaceous. So once you get to what they called the tertiary back when I was in high school, we now call the Paleogene period. You don't have any dinosaurs ever, anywhere, never. So you got them in the Cretaceous, but you don't have them after. So here's a picture from Alabama, and you can see you have Cretaceous deposits here, which is called the Prairie Bluff Chalk Formation, which is a marine deposit. And then notice that right here is the dividing point to the tertiary, or we're going to use the word Paleogene, but I want you to always know tertiary includes Paleogene and Neogene, right? That's the old name for the period. They split it up into the two new names. So this is literally the dividing line between the Mesozoic era down here and the Cenozoic era right there. That's an era boundary. Now, Cretaceous obviously starts with C, but we use the abbreviation KT to stand for Cretaceous Tertiary, right, boundary. And again, I want you guys to make sure you understand now that we don't treat the tertiary like that anymore. We treat it as the Paleogene and the Neogene periods. But the old way of doing it was call it the KT boundary. That's the line right there. That is the KT boundary. Now, all right, so fact number one, no dinosaurs younger than the Cretaceous. No dinosaurs ever from the Cenozoic. No dinosaurs ever from the Paleocene. Okay, fact number two, observation number two. Again, independent analyses from lots of different scientists all over the world. They show that the KT boundary layer, that very thin layer in some cases, was super rich in a very rare type of element called iridium. Iridium is a rare earth element that turns out is most common in outer space on asteroids. So the fact that we have a very anomalously high amount of iridium on Earth strongly suggests that layer got there due to a meteor impact. And that iridium, iridium, is one of the big testaments to that. That's fact two, or observation number two. And then observation number three are specialized little structures called microtectites. Microtectites are these sort of little small globular globular particles that are formed as a result of meteor impacts. It's when those grains of sands and stuff go through that melting and deformation and metamorphosis, they come out and are ejected through very rapid velocity, and they form into these small sphericals called microtectites. That's the third major piece of evidence. So those three combined told lots of different independent researchers, hey, we likely are looking at something that caused the extinction of dinosaurs. It's very much tied to a meteor impact. Now, it then becomes the question of where, okay? So here, these paleontologists are studying the KT boundary on a river in western central Alabama. But you can also go to the Black Hills of South Dakota, and you can see the KT boundary, for example. Here's the Hell Creek Formation. I think this is South Dakota. Actually, this might be like Utah. Anyways, it's far away from the Gulf Coast. Somebody can look it up. Where's the Hell Creek Formation? I think it's the Black Hills of the Dakotas. But in any case, the KT boundary stands out very specifically there as a layer. So no matter if you're in China or if you're in South America or North America, the KT boundary is present all over the world. So that told them that whatever this incident was that involved a meteor, that it was big enough that it likely wiped out all dinosaurs, because the dust that was rich in iridium was carried all around the world, and it settled in a very thin layer, a mantle of dust that settled all over the world. But where that dust was thickest happened to be near around the Gulf of Mexico. So that sort of helped them to start zeroing in on what part of the world this might have happened. Now, another question in the minds of paleontologists was, what do you think the next question should be? What should you look for if you expect a meteor impact wiped out dinosaurs 65.5 million years ago? What do you want to see? You want to see the crater, right? Shatter cones are in the craters. You want to see the crater. Show me the crater. Show me the evidence that there was a murder, right? So they started looking. And, there's decent sized craters all on every continent, pretty much. But one that had the size to wipe out dinosaurs was very difficult to find. Oh, well, keep in mind, there were several of the right size, but they had to be from the right time frame. So geologists could go out to a crater in Arizona and say, oh, that's not right. That crater's, 400 million years old. Or, the Wells Creek structure is not right. That one happened 200 million years ago during the Jurassic. So these easily could be eliminated. They were looking for one of the right size in the right time period, and they couldn't find one. So then somebody says, wait a minute. Remember, guys, let's go back to the drawing board. 70% of Earth is covered by what? Water. Maybe it landed in the ocean somewhere. That's when they began to think about it in a different light. So then you would say, okay, well, if there was a massive meteor impact in the ocean, you might expect massive tsunami deposits as well, right? You would expect, torrents of water, maybe 1,000 feet high to wash up on the shore of America or wherever, carrying with it rocks and logs and debris and having a devastating effect. So in South Alabama, along the Tombigbee River, this is one of the counties, by the way, that SGI works in a lot, Sumter County. But right here, you can see there's the KT boundary just 30 feet away, right? That's the next layer above that's been washed away by the river. But look right here underneath this shelf. There's the tsunami deposits that you would expect. The broken chalk clasts, the broken fragments of rock washed up in a tsunami debris. And keep in mind, this was pretty far inland, for this time period. This is kind of, I guess, right at the coast. So finally, I think in partnership with the Navy, researchers who were mapping the bottom of the ocean floor using sonar, sending signals down and sort of mapping the ocean floor, That was one of the ways they originally found it. Now we have other kinds of lines of evidence that have been published more recently. So it's thought, well, the actual impact site is right here, partially on the Yucatan Peninsula and partially in the Gulf of Mexico. You really can't readily see it, just by looking at it by eye, but there is a slight trough, sort of a slight area of depression on the outermost ring that happens to coincide. If you know anything about the Yucatan, it's a heavily limestone dominated region. Lots of sinkholes, which they call cenotes. And these sinkholes, which are common throughout the area, form a distinctive ring right around the edge of the lower rim of the Chicxulub crater, as it's called. Chicxulub crater. And then from the sonar mapping of the U.S. Navy and other partners, they actually been able to map the extent of the meteor impact, which is massive. This is an artist rendering showing what it might have looked like, in prehistoric times. Very large, perhaps 150 kilometers wide. The impact affected an area 20 kilometers deep, very, very deep. How big was it? Well, by comparison, this was an asteroid that hit the Earth 3.2 billion years ago. You can see it was about 10 times the size of Mount Everest. Here's the kind of crater that it would have caused. But the Chicxulub impact, it was just slightly smaller than Mount Everest. It was 10 kilometers or 6 miles wide. And it would have created a crater roughly the size of the big island of Hawaii. Well, I don't know about you guys, but that's a fun lecture to go through. I think, just realizing that I remember the day I first read, and it's all there in your book, right? That glorious textbook that I know you all are just reading, feverishly before each class, right? It's all there. But I remember the day I read that there was a tsunami, the remnants of tsunami deposits just 4 hours south of Clarksville. I was like, wow. That's so super cool, man. Anybody have any questions here before we wrap up the Cretaceous period? And we're going to go into, finally, the Cenozoic. We're actually going to begin the Cenozoic today.